Okay, so these are the 5.3 notes. So we've been learning that for a reaction, you can have 0, first, or second order, and that kind of describes how fast the reaction is going based off the concentration values. Now, there are graphs that you might be asked to analyze, and so we are going to kind of talk about those. So if you have a 0 order reaction, and I know on our notes before, we kind of already talked about this on the backside here, that if you have a 0 order, your rate stays the same when the concentration varies. So it says what happens to the rate when the reactant doubles. So it's talking about the concentration. So if the concentration is doubling, well, the rate will just stay the same. So for this one, we're just going to say stays the same. That's how we know it is a 0 order reaction. Then it has a rate law. So if we are talking about a 0 order, the reaction is going to be rate equals K. And then let's say A is our reactant, A, and since it's 0 order, it's going to be to the 0 power. Well, anything to the 0 power is 1. So you can also see it as rate equals K because A to the 0 is 1, so 1 times K will just be K. Now, if you integrate this, I don't know if you guys talked about integration yet in your math class, but that has to do with calculus. So for this equation will be given to you, but it is a concentration of AT minus the initial concentration, which equals negative KT. So that is the equation for it. Now, this kind of helps us figure out the graphs, this equation. So here is the graph for a 0 order reaction, and it's asking how does the slope of K, so it is a linear graph because it is a straight line, but K has a negative slope. So for this graph here, one way that, and I'm probably going to quiz you guys on this next week, for the graphs, if it just has, for the y-axis, if it just has the concentration of A, B, C, whatever you're given, you're going to have to know that that is 0 order. And the reason why is because the rate is directly proportional to it. So A is the concentration, and if that is the units for the graph, then you're going to know it's a 0 order reaction and it has a negative slope. So that's for 0 order. If we have first order, remember that first order, if it doubles, then the rate also doubles. If it triples, the rate also triples. So since it's saying the reactant doubles, that means it's going to be exactly the same for a first order. So that means that it is also going to double. Now the equation for first order is rate equals K times the concentration of A. Since it's first order, we would put 1 as the exponent or just leave it. Now, the integrated rate law, that's calculus again in order to get this graph. It is ln AT minus ln, which is the natural log, of A. Let me rewrite that. Of A0, which equals negative KT. Again, it's negative. It's a negative slope. It's also linear too. So it's kind of the same as the 0 order one because it says negative slope and linear. How we would tell the difference at its first order is that the units for the y-axis, I don't know if I said x-axis up here, I meant y. For the y-axis is going to be the natural log of the concentration. If you see ln of A or ln of B, ln whatever, you're going to have to know that's first order. So that's kind of just like memorization. Then for second order, what happens for second order? Okay, for second order, if the rate doubles, if you remember from our notes here, if I flip them back a page, For second order, if the concentration is doubled, then that means you're going to take 2 to the square and the rate's going to increase by 4. Let's say your concentration is tripled. You do 3 squared, the rate's going to be by 9. So since it doubled, that means my concentration is 2. We raise it to the power of 2. That means my rate had to be by a factor of 4 or it quadruples. Okay. So then rate for this equals a squared. And then the integrated law for the graph is 1 over the concentration of A T minus 1 over the concentration of an initial equals KT. For the slope, it's also going to be linear, but this time it's going to be a positive line. So K is a positive slope. For second order, you have to know that if you see 1 over any kind of type of concentration, that is going to be a second order reaction. Okay. Question 2, it says, what is the purpose of an integrated rate law? And then what does concentration of A little t and concentration, I guess 0, we could say. So the purpose of it is to analyze the rate given the concentrations over time. AT, that's just the concentration at some time, whatever that T is. And then this little 0 means initial, so it's the initial concentration. I don't even know if I could spell. There we go. Initial concentration. Okay, for question 3 now, I know it's a little bit hard to see, so I'll try my best to explain it. I'm going to zoom in. It's going to work. Okay, it says nitrogen dioxide is produced as a byproduct of combustion of fossil fuels in internal combustion engines. At elevated temperatures, NO2 decomposes according to the equation below. Here is our equation. It says the concentration of sample of N2 is monitored as it decomposes and is recorded on the graph directly below. The 2 graphs that follow it are derived from the original data. Explain how the graphs indicate that the reaction is second order. So we need to figure out of these 3 graphs that are given, which one is second order and how do we know that? So if I go back up to our notes up here, where we find second order, we should find a graph that has a linear line, but it also is a positive slope because that means it's second order. Also, for second order, our unit should be 1 over a concentration. So if I look at all my options that are given here, I know it's kind of hard to see. This graph, this is pretty clear to see though, this graph is the only one that has a linear line that's a positive slope and it's linear. Okay, so this graph right there. Now we have to check units. This unit right here, I know it might be hard to see, but it actually does say 1 over the concentration. So for letter A here, we know that it's second order because it's 1 over NO2, and that means it's second order, but also we know it's because it's a positive slope. Oh shoot, you can't see that. I just wrote, oh no, wrong way. Holy moly. 1 over N2 is second order. That's how we know that this graph is second order. It's a positive slope and it is linear. So that's why what I'm saying above, that it's a really good idea to start memorizing those units for the graphs because then it's easy to tell. Write the rate law for the decomposition of NO2. So for the rate law, very simple. We're going to say rate equals, it says it's for NO2, so I'm going to put NO2 in brackets. It is second order. So since it's second order, and that is my only reactant, I'm just going to raise it to the second power. So that is my rate law for that one. Okay, if I flip the page now, we have more examples to do. Okay, so this one's kind of hard to see too. I'm so sorry. Printer kind of stinks. Okay. So for the question, it gives us a balanced chemical equation. It gives us the enthalpy change. It's negative. We learned about that. It says decomposition of H2O2, so hydrogen peroxide, is represented by the equation above. A student monitored the decomposition of a 1.0-liter sample of H2O2 at a constant temperature of 3 Kelvin and recorded the concentrations as a function of time. The results are given in the table below. Okay, awesome. Which of the following statements is correct? Interpretation of the data regarding how the order of the reaction can be determined. Well, I know it's really hard to see, so I'm just going to kind of tell you. The options would be B, and the reason why it would be B is because, first of all, in the problem, it mentions linear data. That's what we want regardless of the order. Okay, so linear data. And then what we can say is that it talks about how the units are going to be ln of H2O2. And we know that if it's the natural log right here, that means it's going to produce a linear line. So we know that that is going to be a straight line. So that would be the best option. The other ones talk about different things, but none of them put together the right units with the description of a straight line. So if like this option said the natural log of H2O2 gives a curved line or whatever, we would know that's not correct because they all give a straight linear line. Okay, next problem now. It gives us an equation. It tells us we form some products. I guess it goes from blue to colorless when you go to the product. So it says blue food coloring can be oxidized by household bleach to form colorless products as represented by the equation above. A student used a spectrophotometer set at a wavelength of 635 nanometers to study the absorbance of food coloring over a time during the bleaching process. In the study, bleach is present in large excess, so the concentration is essentially constant throughout the reaction. So we kind of talked about absorbance and wavelength in one of our other units. So for this, we want to pick a graph that is going, well, based off this, it says based on the graphs above, what is the order of the reaction with respect to the blue food coloring? Well, all the orders, first or zero, first, and second, they all show linear lines. So that means I'm going to have to go to the graph that has the linear line. And then we need to figure out what are the units. So then I'm going to go right here. And my units for this are natural log of the absorbance. I'll write that out. That's what that says. Okay. So natural log of the absorbance, those are the units. So natural log of the absorbance, if I flip to the front side, which one has those units out of these three graphs with the straight line? Well, ln that means it has to be first order. And it's a decreasing slope too, so that's good. First order because of the units. Okay, so these questions were kind of really easy to do as long as we know what are the units and what the graph should look like for each order. Next video. For College Board here, it says explain in your own words and using the picture, what is half-life? So this is really cool because it has to do with radioactive decay. So when we talk about half-life, radioactive decay should come into mind. So that's when we have radioactive material. So like uranium, iodine is even used in the medical field. So that stuff is kind of cool to do, radium, whatever. For half-life, the definition of it is for half the original sample to decay. So it is time, so half the sample for the original, or half the original sample to decay. So in these pictures here, if I was going to count up all these dots of particles that I have, it actually comes out to 20. So there are 20 dots there. Now, what is half of 20? Half of 20 is 10. Half of 10 is 5. And that is how many particles or atoms we have in there. So that means every 40 minutes, it takes half the sample to decay. So my half-life is 40 minutes because that is how much it takes for half the sample to decay each time. First order reactions are what we're going to worry about for half-lives. Okay. So there is an equation. It says T half equals 0.693 divided by K. This is half-life. You can calculate half-life, and all you would have to find is the rate constant, or I could give you the rate constant and you would have to find the half-life. On to the next couple problems here. Okay. It says the radioactivity of a sample of iodine 131 was measured. The data collected are plotted on the graph below. Determine the half-life T 1/2 of I-131 using the graph above. Okay. So we need to figure out what is the half-life. So I'm going to go to this graph here, and I know it's kind of hard to see. But we start with 16,000. That's my original sample. So I start with 16,000. Now, for half of it to decay, that means I would divide this number by 2 for half of it. That means 16,000 divided by 2 is 8,000. So I go find 8,000, which is roughly right here. I line it up. My time is on the X. That means it took 8 days. So let's make sure that another 8 days, that's the other half of the sample. So 8 plus 8 is 16. So I'm looking right here at 16. That means I have 4,000. So if I divide 8,000 in half, another half-life, that means there should be 4,000 left over. And which, if I go back to the graph here, there is. So that means my half-life is roughly 8 days. So for this one, it would be 8 days. So for half the sample to decay. D, it says the data can be used to show that the decay of I-131 is a first-order reaction as indicated on the graph below. Label the vertical axis of the graph. Okay, so it tells me that it is first order. If I go to my original notes, if it is first order, that means my units for my graph should be natural log of A or of the concentration. So I'm going to say ln of decay. Okay, so natural log is for a first order reaction, so I just labeled that. What are the units of the rate constant? Well, if it is a first order, that means it's days to the -1. And then explain how the half-life of I-131 can be calculated using the slope of the line. Well, you could K equals -m. So you can find the slope. And then you would plug that information into the half-life equation. And then that's how you would find it. Okay. Next problem. Almost done here. It says the rate constant K for the decay of the radioactive isotope X, according to the equation above, is 2.3 times 10 to the -2 days, inverse days. The slope at which the following graphs is correct for the decay and could be used to confirm the value of K. So I want to know which graph is correct. So, of course, we have 0, first, and second order. That means it has to be linear. So that graph does not work. That graph could possibly be it. This one could possibly be it. This one and that one. Okay, now we have to look at units. So if you have 1 over x, I go over here to my original notes. If I have 1 over the concentration, here's 1 over the concentration, that means it is, oh shoot, it just went out. Did it just end the movie? okay, there we go. If it is what? 1 over, we said, if it's 1 over the concentration, that means it is second order. Well, if it is talking about a radioactive isotope, that means half-lives and radioactive isotopes are only for first orders. Okay, so if I go back to the front then, so these two graphs will not work. Now, if I go to first order should have natural log of A, and the slope should be going down, negative. That's for first order. So if I find the graph that has that, it would be C, because it is a radioactive isotope, and when we talk about radioactive stuff, that's first order. Last problem here. Okay, the ammonium salt is a product of the decomposition of urea. They tell us there's some data in here. They want us to explain how the data supports the student's proposed rate law. So if I look at the student's rate law, that means it's first order, right? Because technically this would be 1, so it is first order. So how do we know it is first order? Well, if it is first order, doesn't that mean that your original sample should decrease by half and then decrease by half again for the same amount of years? I think so, or time. So let's go to the data here. I start with 0.100. 0.100 divided by 2, or half of it, is 0.0500. That means it took 10 years. Or no, sorry, hours, not years, 10 hours. Okay. 0.0500 divided by 2 is 0.0250. There's that. Well, from 10 to 20, that's another 10 hours. So that means that according to this has to be first order, and we know that because the student said that also, but it's because, to explain why that happens, it's because the urea decreased by half each time for 10 hours. So that means it has to be a first order. Okay, next one, it says using proposed rate law and the student's results determine the value of the rate constant include units. Okay, so we have to determine K. Well, it's kind of like a half-life problem, so we're going to use the data for that. So T 1/2 equals 0.693 divided by K. Remember, that was the one we originally started off with. We know that time, according to this data, is 10 hours. So that means 10, I'm going to plug that in for T, equals 0.693 divided by K. If I solve for K algebraically, move it over to the left, and then take 0.693 divided by 10. That would equal 0.069 hours, and that would be your K. Okay.